Hello, my name is Ryan Pham, and this is my Lab 2 for Physics 2211, and my topic today is motion of a falling object. So our purpose of the experiment is to observe the motion of an object that is dropped from rest and falls somewhat slowly, straight down. We also want to create a position versus time graph for the theoretical and experimental data. We also want to compare the accuracy differences when more forces are considered in our theoretical examples. The fundamental principles that we mainly focus on were based on the Newton's second law and the principal equations regarding gravitational and drag force. This was done by recording a wallet being dropped. Using the tracker software, I analyzed and recorded the data from the video. I then created two models using the GlowScript software describing a theoretical model with and without drag. The graph that considered both gravitational force and drag force ended up being more accurate in predicting the experiment compared to just considering gravitational force. Here's the video I used for this experiment, which showcases my wallet being dropped. Using Tracker, I first calibrated my video using the height of my laptop being 0.271 meters. I then placed the axis at the starting point of my experiment in order to create a point of origin. Something to take note is that both of my lines used for the calibration and axis were tilted by negative 0.3 degrees in order to consider that the video was taken at a slight angle. To represent my data, I used 11 evenly spaced time intervals to record the position of the center of the wallet. Another note to consider is that the recording of the position occurred right before the wallet was released in order to accurately represent our zero velocity. On the left of the screen, a portion of the data gathered can be seen at intervals of 0.033 seconds. Additionally, we can see that our position versus time graph is not linear. This means that there were forces acting upon our object unlike Lab 1. With the help of Tracker, I was able to find my initial position vector of 0 meters and my initial velocity of 0 meters per second. The total duration recorded of the object was 0.367 seconds, and the total displacement of the wallet was 0.97 meters. So now let's talk about the scientific principles. The first principle we must consider is the net force in Newton's second law. We can consider our net force to be equal as the change in P over the change in T. This can also be described as our force of gravity being added with our force drag. Speaking of our gravitational force, the equation for it is equal to negative mg times j hat. Our mass being 0.044 grams, as in the wallet, our gravity being the 9.8 newtons per kilogram, which is calculated through our gravitational law, and our j hat is equal to our direction. For turbulent drag force, we have negative b times the speed square times the direction of our velocity, and the b is represented as our proportionality constant. So as you can see in the picture on our right, the wallet would be our system for this experiment, and everything else would be counted as the surrounding. So our force of gravity downwards would be counted, and our force of drag, which is counteracting our force of gravity, would also be counted in our surrounding. And once those are added together, that will equal our net force. So using the GlowScript model, we can simulate what the predicted values of the wallet falling would be if only gravity were acting on it. To compare this model with our video analysis, we must use the same values, including the mass, initial position, initial velocity, and length of time that were found in our experiment. Then we also add in our net force, or specifically gravitational force, in this scenario, our Newton's second law, and position update formulas into our code. This code then produces a graph that predicts the position of the wallet at its respective time. To implement drag, we can use most of the same values as our gravitational-only model, but we must implement a proportionality constant for our drag force, which is b. Then we also must implement our turbulent drag force equation when considering our net force. With this, we can calculate our new net force by adding the negative force of gravity with our counteracting or positive drag force. As a result, the updated net force with drag was shown to be more accurate to our experimental values compared to when it was only gravitational. However, there are still discrepancies that have affected our data. This can be done by human error when dropping the wallet or specifically using Tracker, but this could also be possible from other random forces, including wind from air conditioning. So to improve our experiment, we can use smaller time frames between each gathered data point to get more accurate results, and by having a more inline camera angle. Now onto the reflection questions. Which models, if any, predicted a terminal velocity? In our scenario, neither. since both of our velocity versus time graphs showed linear results. Since the terminal velocity has equally balanced forces, our F net would equal 0 during terminal velocity. Terminal velocity will show constant velocity and would plateau on our graph. So for our second question, I predicted that it would be the same because the gravitational force has a discrete value as it is mainly impacted by the unchanging mass. The drag force needed would still be the same to reach terminal velocity. However, terminal velocity would be reached quicker than if it were at rest compared to if force was added on while it was dropping, at the beginning of when it's dropping. Thank you for listening.